Alright guys, so this is going to be a video about forces and springs. Springs come up fairly often in our lives. You know, you think about the springs in the car, on the suspension of your car. You know, we got the slinkies, and a lot of mechanisms that we use in our lives, whether you realize or not, involve springs. So when we look at springs, we realize that when we stretch or when we push a spring in, that it's going to exert a force back on the applied force. So what this video looks at is the equation that tells us how to calculate that force. And it's a very simple equation. It's called Hooke's law, and it has the form force is equal to negative K delta X. And I'm going to explain each of these variables. So we imagine that we have a spring, and it's going to have some equilibrium position. Okay, so we'll make that equilibrium position 0 meters. Now if we take a force, we apply a force this way to it, it's going to stretch out this spring. It's going to stretch that out. It's going to stretch at a distance that we call delta X. So this delta X is the amount of stretch or compress, or stretch or compression, and it has units of meters. So again, this isn't the length of the string. Let me make that very clear. Delta X is not the length of the string. It's how much you stretch or compress it. Now, the force is, in this equation, is actually the force being applied by the spring. Okay, so it's by the spring. And for that reason, we have a negative sign here, because the force that we apply, we'll say, is positive. So in this case, positive is that direction. So the force that we apply is positive, and the force that the spring applies to be negative. It's always going to be opposite direction from the force that we're applying, so we have a negative sign there. Okay, so this force, strictly speaking, is the force applied by spring. But you'll see in the two problems that we work that very often we drop the negative sign and we just put the force that's being applied to the spring in for this. And this has units, obviously, of newtons. And then K. This K is the spring constant. Okay, and this is probably the one variable that is most confusing. So this is the spring constant. It has units of newtons per meter. So let's talk about the spring constant a little bit. So the spring constant indicates how stiff a spring is, or how hard it is to stretch or compress a spring. The larger your spring constant, the more difficult it's going to be to make that spring stretch or make that spring compress. So again, looking at our cars, the suspension of our cars, those springs, if you ever looked at those springs, they're like really like kind of thick springs, and it's very hard to make them stretch or compress. And it's a good thing, because if it was easy, then then they wouldn't support our cars. Essentially, our cars would just would smush them, and they would, you know, hit our tires. We get over a bump in our car, we just go all over the place. So sometimes it's really good to have a large spring constant. So the ratio, as we saw, this ratio is going to be newtons per meter. So what that's saying is this number, the spring constant, tells us how many newtons we would need to apply to stretch that spring by 1 meter, even if they couldn't stretch that far. So say we have a very thick spring, here, and this could have a K of maybe like 3,000 newtons per meter, which is a fairly large spring constant. And maybe we have another spring that's much thinner, and this would have a K of maybe only 200 newtons per meter. Okay, it'd be much easier to stretch this spring than it would be to stretch the 3,000 newton meter spring. Okay, so again, the spring constant of a spring tells you how difficult it is to stretch or compress a spring. And sometimes we don't want the spring to be able to stretch or compress all that much when we apply a force to it. Okay, so I have two really honestly kind of simple problems just to show you how all this works. So again, Hooke's law, it's what we use when we have springs involved in our system. So say that we want to know how much force is needed to pull a spring with a spring constant of 20 Newton meters, a distance of 25 centimeters. So we look at the spring. Okay, we imagine originally it was right here. We apply some force that we don't know. We apply some force to it, but we know that we stretch it a distance of 25 centimeters. So being a spring, we know that we're going to have to use Hooke's law, so F. Now, because we're going to solve for the force that we're applying, we're going to drop the negative, and we're just going to put K delta X. We want to solve for the force. We know K is 20 newtons per meter, and the delta X, now we have to be careful here because this is going to be in meters, or it has to be in meters, so this is going to be 0.25 meters. So we multiply those two together, and we get 5 newtons. The meters cancel out. Always put units after your numbers. Okay, it really does help you. So anyway, we would have to apply 5 newtons of force to get this to stretch 25 centimeters. Not too bad, right? Okay, this would be number 2. So another problem that we could see is a problem that asks us to solve for the spring constant itself. Okay, so in this case, we'll have a spring, and it was right here. We apply 500 newtons of force, and now we know the force that we're applying to it. And we know that it stretches 10 centimeters, but what we don't know is what the spring constant is. So even though we are not stretching at the full meter, we can still solve for what force, kind of what this ratio of newtons per meter is. So we're going to go back to Hooke's law. Again, this is the force that we're applying, so we're going to drop the negative. K delta X. I'm going to solve for K by dividing delta X, both sides by delta X. So this will be F divided by delta X. And so we can see that K is this ratio of 500 newtons divided by 0.1 meters. Again, we have to use meters. And so we get a K of 5,000 Newton meters. Okay, which is, it's a fairly large K. All right, so that's, even if we don't stretch the spring by 1 meter, if we know the force we're applying and we know how much it's stretched or compressed, we can solve for the spring constant K. And as I said, if you're designing a piece of equipment and you have to use springs, that's a useful thing to know, is how much the spring will stretch and compress with any applied force. So I know these two problems are fairly straightforward. We'll do some more problems in class, but I hope all this made sense. And if you have any questions, please feel free to ask.